All right, well, here is the last lecture that I'm going to record for you, and it is for our class tomorrow. And this chapter is not doing what the previous chapter did, and that's trying to explain evidence in an alternative way that might be consistent with a short age geological position, but this is presenting evidence that seems to indicate that the Earth is not nearly as old as conventional geology would say. Some of these evidences do point to the Earth being thousands of years old, but many of them just point to the Earth being far less than hundreds of millions of years old. So, what are some of these evidences for short ages? The first evidence I want to talk about is catastrophism. So when Charles Lyell published his book on uniformitarian geology, it became basically the paradigm for about 100 years, all the way up until we started to find evidence of very significant geological features happening in short periods of time. Some of this work was done in the Grand Canyon, studying pictures taken 90 years apart and realizing that for most of the canyon it was completely unchanged, but in some areas you had very significant amount of change, indicating that there are these catastrophic events separated by long periods of stasis. A lot of this work was also done in the Pacific Northwest, studying the Columbia River Valley and some of these geological features. And again, that looks like they were evidence of a flood from a glacial lake where a glacial dam failed and you had an enormous amount of water spill out and carve up the land very quickly. And so there's just a great deal of evidence that the geological record is not just a slow, it's just not a series of accumulating sediments in the same way we're accumulating them today, but rather is a series of catastrophic events separated by either long periods of time or very short periods of time, and many of those catastrophic events may be part of the same catastrophic event. And so this is what's challenging about geology from either perspective, is with this evidence of catastrophes larger than anything we have a documentation of how it works. A lot of this is fluid, and our explanations are fluid. But anyways, this evidence for catastrophism and looking through the geological record, looking like that those catastrophic events are becoming less frequent and less widespread, are evidences that the Earth is not nearly as old as conventional geology would suggest. Not necessarily that the Earth is thousands of years old, but definitely that it is not as old as conventional geology would suggest. Another couple other pieces of evidence. One are what are called density flows. And so when water is flowing over sediment, the top layers of sediment tend to become suspended in the water column, forming what's called a turbidity current. And it deposits sediment in a very particular way, and it leaves a signature in the rock. And so we are discovering these density flows all around the globe, suggesting that a great deal of the sediment in place was not deposited by wind, but rather was deposited by water, evidenced by these turbidity flows and on a global scale. Another piece of evidence, rates of erosion and sedimentation. If you measure the amount of material being carried away from continents by rivers, current estimates are that you should be able to erode all of the continents down to sea level in about 10 million years. And so obviously that's an issue, because if the Earth is hundreds of millions of years old and the continents have not been eroded down to sea level, then our current rate of erosion must be much greater than what it was in the past. And so here's an indication of that in this graph. You have basically here we've got a logarithmic scale on the x-axis. On the y-axis, we have also a logarithmic scale. And so what we see is that the rate of accumulation of sediment actually it seems to be that this rate is not constant. That what we have today is many times greater than what we had in the past. And we'll talk a little bit more about this in the next slide. But also, if you measure the amount of sediment carried by rivers away from the continents into the ocean, you should be able to fill the entire ocean with sediment in I think somewhere around 100 million years. And again, this has obviously not happened, and so our current rates of erosion and sedimentation indicate that they are either way faster than what they've been in the past, and I think most geologists would suggest that's because of human agricultural practices, or that the Earth is not nearly that old, and so even though our rate of erosion and sedimentation would erode away all the continents in about 10 million years and fill the oceans in about 100 million years, it's not an issue because the Earth has not been around nearly that long. And so I think if you took the entire Phanerozoic, so Paleozoic, Mesozoic, Cenozoic, and you divide the largest section of that, which is about 2,000 meters, by the amount of time, you find that sedimentation rates would be about 0.001 centimeters a year. Which is about 1,000 times slower than current sedimentation rates. And so the suggestion for that from conventional geology is that what happens is something like this. You have a sedimentary rate consistent with present sedimentary rates, but most of it gets eroded away before the next layer is deposited on top of it. And so 99.9% of the sediment deposited, it gets eroded away. What's interesting here is you find very little evidence of that. There's a lack of missing rock. So you don't have a significant amount of evidence that we're missing materials. Instead, what you get is that one deposit butts right up next to the next deposit. Now, there are areas where you do have evidence of erosion because of the next layer penetrating down into the previous layer. But what the authors of the textbook, Dr. Brand and Dr. Chadwick, suggests is not to appeal to erosion unless there's obvious evidence of erosions. And there's very little evidence of this. And here's another evidence for short age is A, B, C, and D provide evidence of what these processes should look like if there is significant amount of erosion happening like this. Erosion doesn't leave these nice flat plains, but erosion carries or develops valleys in the material as water finds the path of least resistance. And so what you would have if you had this degree of erosion is this is what your fossil record should look like, or your geological column should look like. But this is pretty much what it looks like. Again, very little evidence for erosion. And then we need to account for some reason why the sedimentary rate was 1,000 times slower in Earth's history than it is now. Now, so this suggests that the Earth is not as old as conventional geology suggests. However, you do have to note that if you're going to lay down the entire Paleozoic and Mesozoic within a single year, that the rate of sedimentation has to be about 200,000 times greater than it is now. Now, we've seen before, we've talked about this before, small amount of water, little sedimentation and erosion, a lot of water, a lot of sedimentation and erosion. So if you have a global flood, there are ways and mechanisms in which you could explain how that might happen. Some additional evidence for short ages is the progressively localizing of deposits as you move up the fossil record. So when you go to old deposits, Paleozoic and Mesozoic deposits, they are huge, huge, covering hundreds of thousands of square miles. And as you move into the late Mesozoic and early Cenozoic, these deposits get very small, and so the idea here is from a short age geology is here you're looking at something that looks a lot like a global event, or at least a regional event. And here you're starting to get progressively smaller deposits. The explanation from conventional geology is you get these uplifting events that form these mountain ranges. And so you, instead of having a massive basin for depositing sediment, you have smaller basins. But this doesn't work when you realize on a global scale that there are very characteristic elements of Cambrian rocks everywhere where you find Cambrian rocks, illustrating that there's something global happening when you deposit those rocks. So again, further evidence that the Earth is young, and those materials were deposited in some kind of a global event. This one we've talked about before, mass burial events. And so letter A is what you actually find, where you find these turtle deposits, and you find them right above a limestone. So when a lake forms in this area, providing a suitable environment for turtle populations to grow, you start getting lake deposits, and then you get a lot of turtle deposits. And then some time passes, and then you get another limestone deposit from a lake, and then turtle deposits, evidence of rapid burial, and so not slow accumulation of sediment. This is what you'd expect to find in your turtle deposits if what conventional geology teaches us is actually true. And what's interesting is the age of this is determined primarily using radiometric dating. And so the rocks here are going to date about 10 million years older than the rocks at the top, and yet there's enormous evidence for a very rapid biological and geological event. Further evidence of short ages is the lack of bioturbation in much of the fossil record. So here's what a typical soil looks like, with organisms burrowing down into the sediment and essentially erasing what you would call the bedding patterns, where you have these very unique and discrete layers of sediment. But as animals dig through that, they will erase that bedding. They will and then just mix all of these soils. And so here, you can see a fossilized area with a high amount of bioturbation. Letters D and E are what you typically find in the geological column. Very little evidence of bioturbation, an indication that these sediments were not around for a long period of time underwater, allowing for an environment like this, but instead were buried very rapidly. Further evidence that these deposits are not nearly as old as conventional geology leads us to believe. Last two pieces of evidence I want to talk about. One is taphonomy. Again, this is something we've talked about before. When you study how rapidly skeletons disarticulate and animals decompose, you realize that we have a problem whenever we're going to fossilize something. It either needs to be buried in an anoxic environment. Well, we've talked about that before. That really doesn't slow the rate of decay. Also, there's very little evidence that these organisms were buried in anoxic conditions, because you find them buried with aerobic bacteria and other forms. But organisms decompose very rapidly, and so there's enormous evidence whenever you have a well articulated skeleton, you have evidence of rapid burial. Now, what's interesting is that is also a challenge to short age geology of how do we explain the poorly articulated skeletons buried along with really well-articulated skeletons, because the well-articulated skeletons require rapid burial, but the poorly articulated skeletons indicate that they kind of floated for a while. And so how at the same time in the same deposits do you get, rapid burial and a body sticking around for a while to decompose? There are some challenges. The last piece of evidence I want to present are finding biomolecules, proteins, even DNA inside of these fossils that are dated to be tens or hundreds of millions of years old. These biomolecules have a very short half-life, on the order of maybe tens of thousands of years, hundreds of thousands of years at absolute most, and yet we find Paleozoic fossils that have evidence of biomolecules. And this, again, is evidence in favor of a short age geology, that what we're looking at in this geological record is not nearly as old as conventional geology would predict. All right, so as you prepare for class on Wednesday, what I want you to do is be prepared to talk about these evidences in favor of short age and thinking about an alternative explanation for some of these for conventional geology.